In this lesson, we will continue with another topic in the matrix, which is system of linear equations. So this will be the last topic for chapter matrix. The system of linear equations consists of a number of linear equations where we can write it as in terms of this form. So this is called as the system of linear equations. So this we have a11 x1 plus a12 x2 plus up until a1n xn equals to b1. So a11, a12, a1n is the coefficients of the variable of x1, x2 up until xn. And b1, b2 up to bn is the constant. So in this topic, we will learn 4 methods to solve the system of linear equations. The first one is we use the method of elimination, where there are 2 types of method that will be used. The first one is using Gauss elimination method. The second one is using Gauss-Jordan elimination method. And then for the second method, which use the matrix method, where there consists 2 methods. The third one is inverse matrix and Cramer's rule. So I'm going to show you all these methods to solve the system of linear equations. The first method is Gauss elimination method. For Gauss elimination method, this is the step to solve the system of linear equation using Gauss elimination method. First of all, from the system of linear equation, we will transform the system into the augmented matrix, where the augmented matrix is the combination of the column from matrix A and matrix B. And then in the Gauss elimination method, it consists of 2 phases, where the first one is the forward elimination phase and the second one is back substitution. Once we have the augmented matrix, we will apply the forward elimination, where forward elimination transform the coefficients matrix of A into an upper triangular matrix. Then we use the back substitutions, which means that the last equation will be solved first. So in order to get x3, we have to divide d3 over a33. And then we solve the second row in order to get the value of x2. And the last one is we solve the last equation, which is the first row, in order to get the value of x1. So now let us try see the example in order for you to understand how to use this Gauss elimination method. So for the first one is solve the following system of linear equations using Gauss elimination method, given the system of linear equation as this. Okay, now what we need to do is that we have to transform this system of linear equations into the augmented matrix. But before that, we can draw this, or we can transform this into matrix system. So for the first one, we want to transfer into in terms of A, x equals to B, where A is the matrix of coefficients of x, and x is the variable of x, y, and z, and B is the constant of the right side. So our A here consists of all the coefficients of x. So here we will write for the first column, it will be 1, 3, and 2. where this is the coefficients for x. And then for the second column, it will be the coefficients of the variable y. So here we will have 2, 8, negative 1, where this is the coefficients of variable y. And the last one will be the coefficients of the variable z. So this will be the value for the third column, where will be negative 1, 9, and 2. So now we have the values for matrix A, or we call it as coefficient matrix. Then we multiply with the variable, where our variable is x, y, and z, where this is equals to b, where b is the constant of the right hand side, 6, 10, and negative 2. So our system of linear equation is now can be written in the matrix form. Okay, from here, we can write this matrix form in terms of augmented matrix, where the augmented matrix is the combination of columns from matrix A and from matrix B. So our matrix A is given as 1, 2, and negative 1, 3, 8, 9, 2, negative 1, 2. And here for matrix B is the 6, 10, and negative 2. So this straight line is the indicator of two different matrices that is combined. So the first one will be our matrix A, and the next is matrix B. Okay, now we have transformed the system of linear equations into the augmented matrix. Then what we need to do is that we have to apply the forward elimination, where we need to transform this matrix into the upper triangular matrix. So in order to do that, we have to implement the elimination row operations, where we have to let these coefficients into 0. So for the first step is that we have to make sure the second row is equals to 0. So in order to do that, our R2 first is we want to make sure this will be equals to 0. So R2 will be equals to our second row minus 3 R1. So this will be 1, 2, negative 1. So we just rewrite the first row, and our second row now is equals to R2, which is 3 minus 3 times first row is 1. So this will be 0. And then for the second column, which is 8 minus 3 times R1, which is 2. So we have 8 minus 6, which is 2. And the last one is 9 minus 3 times with the row 1 for the third column is negative 1. So we have 9 plus 3, which is 12. And then for the last column in B, we have 10 minus 3 times 6. So it will be 10 minus 18, which is negative 8. So here we just rewrite the third column, which is 2, negative 1, 2, and negative 2. Then we may want to make sure the third row first column is equals to 0. So our next step is to make sure that our third row, which is R3, equals to third row R3 will be minus with the first row times with 2. So our matrix will be, for the first row, will be the same. The second row will be the same too. And for the third row, this will be 2 minus 2 times 1. So here we have 0, and then negative 1 minus 2 times with the first row, second column. So this will be negative 5. And for the third column, third row, this will be 2 minus 2 times with negative 1. So we have 4. And the last column, which is negative 2 minus 2 times with 6. So here we will have negative 14. So now the last part is that we have to make sure that the third row, second column should be equals to 0. So for here, what we need to do is that our third column should be involved with the second row, because if we use the operation that involve the first row, this will affect the third row first column, because let's say we have to multiply with 5 over 2 R1, this will affect with this. So this will be no longer 0. But if we involve with second row, this third row's first column will be remaining as 0. So here R3 will be equals to negative 5. So in order to get the second column as 0, we multiply, or we make sure that our third row plus with 5 over 2 multiply with R2. So that this will be negative 5 plus 5 over 2 times 2, and the third row second column will be 0. So we rewrite back the first column, the first row, and then the second row, and for the last row, so the first column 0 plus 0, this will be 0, and then this for the second column, this also be 0, and then for the third column, which will be 4 plus 5 over 2 times with 12, so here will be 634, and then for negative 14 plus 5 over 2 times with minus 8. So here we have 20 minus 34. So now we have solved the augmented matrix using the forward substitution, where we have transformed the coefficients matrix into the upper triangular matrix. So now what we can do is that we apply the back substitution, where we solve the last equation first to get the value of z. Okay, so now I'm going to show you using back substitution. So here I rewrite back the final solutions, and then using the back substitution, meaning that we solve the last equation first. We know that the first column is for x, the second column is for y, and the last column, the third column, is the coefficients of variable z. So here this will be 34, z equals to minus 34. So our z will be equals to -1. Okay, then we'll solve the second column, the second row. So here we will have 2y plus 12z equals to -8. But we have known the value of z, so we just substitute into the equation. So here 2y will be equals to 12 minus 8, which is 4. So y will be equals to 2. And the last one is solve the first row. So for the first row, the equation will be x plus 2y minus z equals to 6. Substitute the value of y and z into the equations. We will have x plus 2 times with y, which is equals to 2, minus z, which is -1, which is equals to 6. So here we have x plus 4 plus 1 equals to 6. So our x will be equals to 6 minus 5, which is equals to 1. So now we have solved the system of linear equations where our final solution is our x is equals to 1, y is equals to 2, and our z is equals to -1. Now let us see the second example. Solve the following system of linear equations using Gauss-Elimination method. So in order to solve these questions, first you need to identify what is the matrix of A and the matrix of B. So our matrix is given that it is a coefficients matrix where it is the coefficients of the variable of x, y, and z. So for the first column is the coefficients of x. So our coefficients of x is equals to 1, -1, and 1. And then for the second column, it is the coefficients of variable y. So we have our coefficients is equals to 1, 1, and 3. And for the last column, the third column, this is the coefficients of z, where the coefficients of z is equals to -1, 1, and -1. And then the B matrix is the constant in the right hand side. So this will be 3, 2, and 6. So now we can write the augmented matrix in terms of this form. So we write all the columns in A augmented with the column in B. So here we have 1, 1, -1, -1, 1, 1, 1, 3, -1, augment with B, which is 3, 2, and 6. So in order to solve this using the Gauss elimination method, what we need to do is we need to transform this augmented matrix in terms of the upper triangular matrix. So all the elements in this should be equals to 0. So for the first part is that we solve the second row where this element should be equals to 0. So in order to do that, we have to make sure our R2 equal plus with our R1. So we just rewrite all the elements that does not involve in the operation. And then our row 2 will be 0, 1 plus 1 is 2, 1 plus negative 1 is 0, and for the last column will be 5. For the third row, we just rewrite this back. Okay, then the next step is that we have to make sure the third column should be, the third row should be 0. So here we have our R3 is equals to R3 minus R1. So our metric will be equals to 0 to 0 and 5. And for the third row, this will be equals to 0. And then 3 minus 1 is 2. And then this will be negative 1 minus negative 1, 0. 6 minus 3 is 3. Okay, and then we have to make sure this element should be 0. So in order to do that, we have to involve the third row with the second row so that the first element of the third row should not be affected. So our R3 equals to R3 minus R2, and here our matrix will be 0 to 0 and 5, and the last one will be 0. 2 minus 2 is 0, and the third column is 0. 3 minus 5 will be negative 2. So as you can see here, if we want to use the back substitution method, where we need to solve the last equation here, we will have the left side, which is x, y, and z, multiply with 0. It should be 0 equals to negative 2. So it means that this system of linear equations, or I simplify it as SLE, has no solution because we cannot solve the last part of the matrix. Now, the next method in the elimination method is using Gauss-Jordan elimination method. For Gauss-Jordan's elimination method, so the method is the same for the first step, where we transform the system of linear equations into augmented matrix, where the matrix is the combination of matrix A and B. So our matrix A will be augmented with matrix B. Then, using the elementary row operations, we will eliminate the coefficients matrix, where the diagonal of the coefficients matrix is equals to 1, and the other elements except for the diagonal will be all 0. So we need to transform this augmented matrix in terms of this. Then finally, we use the substitution, where from here we can straight away get the value of variable x1, x2, and x3 by taking the value of the constant in matrix B. So the difference between the Gauss and the Gauss-Jordan is that the n of the coefficients matrix will be in this form for Gauss-Jordan, and for Gauss method, the n of the coefficients matrix should be in an upper triangular matrix. So now let us try example in order for you to understand more about this method. Okay, now we have solved the following system of linear equations using Gauss-Jordan elimination method. Given the system of linear equations is this. So first, what we need to do is we need to identify the matrix of A and also matrix of B. So our matrix from this system of linear equations is given as, where A is the coefficients matrix, so all the elements in matrix A is the coefficients of the variable of x, y, and z. So for the first column for A will be the coefficients of variable x. So here this will be 1, 4, and 3. And for the second column, this will be the coefficients of variable y, which is -1, -3, and 1. And for the final column will be the coefficients of variable z, which will be 1, -1, and 2. And for matrix B, we have the constant of the right hand side, which is 3, 6, and 23. Now we can transform this system of linear equations into the augmented matrix. Where this is in terms of matrix A augmented with matrix B. So the matrix will be in terms of 1, -1, 1, 4, -1, -1, 3, 1, and 2. So this is for matrix A. Augment with B, which is all the columns in matrix B. So here what we need to do next is that we need to apply the elementary row operations for us to get all the diagonal is equals to 1 and the other element except for the diagonal is 0. So for the first part is we try to solve the second row. So here we want to make sure this second row, first column is equals to 0. So our R2 will be equals to R2 minus 4 times with R1. We write the first row and then for the second row this will be 4 minus 4 times 1, which is 0, and then -3 minus 4 times -1, so this will be 4 minus 3, which is 1, and the last one will be -1 minus 4 times with 1, this will be -5. And for the column in B, we have 6 minus 4 times with R1, which is 3, so this will be -6. Now I rewrite all the values, all the elements in the third row. Then our aim is to make sure that the third row is equals to 0. So here in order to get this, we have to make sure that our R3 will be equals to R3 minus 3 R1. Then we rewrite all the elements in first row and second row. And then for the third row, this will be 3 minus 3 times 1, which is 0. And for the second column, this will be 1 minus 3 times with -1. So here will be 3 plus 1, which is 4. 2 minus 3 times 1, -1. And the last one is 23 minus 3 times 3. So here we have 14. Then Next is make sure this third row is equals to 0. And then our third row will be R3 equals to R3 minus 4 minus 4 times with R2. So here our first column will not be affected. It will be 0. And then 4 minus 4 will be 0. Negative 1 minus 4 times with negative 5. So here we'll have 19. And the last one will be 14 minus 4 times with negative 6. So here we have 24 plus 14, which is 38. Okay, now we want to make sure the elements in this row is equals to 1. So we divide the third row with 19. So here we have 1, negative 1, 1, 3, 0, 1, negative 5, negative 6, and the last one will be 1 and 2. Okay, the next step is that we want to make sure this element is 0. Then we apply So in order to do that, we have to make sure that this element in column 1 should be 0. So in order to do this, we have to involve the third row here so that it won't get affected with the first column of the second row. So in order to do this is that our second row must be equals to R2 plus with 5 R3 so that we can get this element is 0. So rewrite the first row and then our second row will be 0 plus 0, 1 plus 5 times 0 and negative 5 plus 5 which is 0 and then the second row should be 1. Okay, and then negative 6 plus 5 times with 2, so here will be 4. Okay, and then the last step, the second last step is we have to make sure this point is equals to 0. Then what we need to do is that our R1 should be equals to R1 minus with R3. So here will be 1, negative 1, 0. And then 3 minus 2 will be 1. 0, 1, 0, 4 and 0, 0, 1, 2. Okay, and the last step is that we have to make sure this element is equals to 0. So in order to make sure that the element in the third column of first row should be 0, we should involve with these two operations only, which involve the second row. Then our R1 will be equals to R1 plus R2. So here 1 plus 0 should be 0. Negative 1 plus 1 is 0. 0 plus 0 is 0. And then 1 plus 4 is 5. And then we just rewrite all the remaining row. Okay, now we have transformed the augmented matrix into this form where all the diagonal element is equals to 1 and the other element is all equals to 0. Okay, now we can just get the value of x, y, z. Since we know that the first column here is equals to x, the second column is y, and the third column is for z. So we basically get the solution of this system of linear equations where our x is equals to 5, y is equals to 4, and our z is equals to 2.